Okay, there you go. We're going to pick up where we left off. By the way, it seems to me like some of you are working way too hard on this quiz. Like, you never had to use the quotient rule at any point. So if you use the quotient rule, you're wasting time.
Yeah, I knew it. I knew it. Just put the negative exponent, whatever the hell is underneath.
What's the derivative of that guy? What's the derivative here?
Well, that's a constant.
It's a constant. What's the derivative?
Zero.
A lot of you are not paying attention to the rules. That's why I have you guys write down the rules. When something is a constant, the derivative is zero. There are no x's here. It's not a function. It's a constant function. So some of you are like trying to apply the log rules, and yeah, you need to pay attention to what these things are. Anyway, let us move on. We can go over the quiz and anything else in the review when we're reviewing for the next test. So we're just going to continue with, I think we're talking about implicit differentiation. So it's 3.5. So we're going to talk about implicit differentiation and log differentiation. And I think that's maybe all we're going to cover in the remaining time. But let's see. So, implicit differentiation, remember when we use that guy? When do you use this?
When you have like x's and y's and basically half the alphabet jumbled into one
Yeah,
equation.
all variables jumbled up. Function not explicitly defined. By that I mean the y value, the y function is on one side by itself, and then on the other side there are nothing but functions of x. Explicitly defined. How did we kind of get around that?
Whenever you're taking the derivative of y, you times it by y prime.
Right, you differentiate as usual and multiply, right, meaning you obey all the rules. The product rule, the quotient rule, the chain rule, they all still apply, but you multiply by y prime or dy dx when differentiating a function of y. And this is, of course, defining y prime. And then solve for dy dx at the end. And that part is just algebra. Now, you may be wondering, and rightly so, what was so special about attaching a y prime when you differentiate a function of y? Turns out there is nothing special. We could have thought of things in reverse and just attach an x prime every time we differentiate a function of x. It depends on who we want to think of as our dependent variable and our independent variable. And I sort of want you guys to get out of the habit of thinking that these variables have some intrinsic meaning. Like, they really don't. They're just dummy variables. We could name them anything we wanted. You know, we just call them x and y for whatever reason. But I could have called them Sam and Shirley. I could have called them anything I wanted to. Right? They're just dummy variables. It doesn't matter. There's nothing inherently about the letter x, which means it's the independent variable. Right? So I want you guys to start to think a little bit more loosely here. Note. Sometimes our variables can have other interpretations. Right, so it's not just the y is always the output and the x is always the input. Right, sometimes that has to be explicitly defined. or explicitly stated. We can have other interpretations of our variables. One important one, which we're going to come back when we talk about related rates, is the idea of parametric equations. I don't know if we're going to use that phrase. Interpretation is rate, right? How fast something is moving. With respect to, when I say the rate of something, what's with respect to? How fast can I consider something to move?
Time.
With respect to time. Right? So if I specifically define my input variable, my independent variable, to be time, then if I find how fast something is moving, I call that a rate. Right? There are times, and again, as I said, we'll come back to this in related rates. There are times when we want to think of x and y as functions of time. Meaning your x is a function of t. You may or may not know what its explicit definition is, and your y is also a function of t. So they are both dependent variables, i.e. they are both dependent variables. And we'll see applications of this pretty soon, in the next couple sections. Right? In this case, when differentiating, you would attach x prime, or dx dt is how we call it, when differentiating an x function, and y prime, or for emphasis, dy dt, when differentiating a y function. Right? So sometimes our x and our y can both be dependent variables, where my input variable, the independent one, is time. And I'm trying to see how the variables x and y change in relation to time itself. How would you know if you want to think of something else other than x as the independent variable? How would we know? Well, there's one. Rate is mentioned. Not rate of change, but the rate. And that's a word that signifies you're thinking of how things change with respect to time. You use that word rate. Another way is the Leibniz notation. So, for example, when you write dy dx, right, there's more. This means, of course, the derivative of y with respect to x. Right? You can read it as that. But then another thing it does, it actually signifies to you who is the dependent versus independent variable. Right? The guy that's on top, that's your dependent variable. And the guy that's on the bottom, that's your independent variable. Right? So So if this notation is used, you can look at the bottom and you can know, oh, x is the guy I'm thinking of as the input, so when I differentiate an x term, I don't have to do anything, but if I differentiate anyone else, I have to attach the prime, right? Because you have to apply the chain rule. That's kind of how you want to think of it. Yes, what's your question?
What would happen if you had more than one dependent variable? Would you write dy,
More than one dependent variable?
Yeah.
Oh, nothing. You continue just as usual.
So
I'm actually going to do an example with more than one dependent variable. If you have more than one independent variable, that takes you to calculus 3. We're not going anywhere near that. But you can have several dependent variables. I'll do an example with you shortly when we have several. Okay. So don't get attached to these variables that x has to mean input and y has to mean output. We can change the interpretation anytime we would like. And one important way we want to change an interpretation is if we're talking about rates, how fast things change with respect to time. That's one of the most widely applicable scenarios for calculus, right? You want to know how things change over time, and this notation will tell you. So, for example, if I say something like xy plus x squared y equals 3, and then I say find dy dx, and I say xy plus x squared y equals 3, and I say something like find dy dt, these are very different. Right? The fact that there's an x here and there's a t here makes a world of difference, right? There's so sometimes I know you guys might think I'm mean when I put things on the quiz. You know, like this guy. You're like, it's just a constant, but you made it look like a function. Why are you trying to trick us? The point is, these little subtleties, these are things I want you guys to practice catching, right? I want you to know when something is a function. I want you to know when something is an independent variable versus dependent variable. Because there are going to be these little subtle clues that if you're not careful, you'll do completely the wrong thing. A lot of times there's a lot of subtlety going on here, and that can change things greatly. Now, the first one, we know how to deal with this since last time. The fact that x is the dependent variable, the independent variable. When we differentiated x, we didn't have to do anything. Now, t is the dependent variable, which means I'm thinking of x as a function of t, which means now if I differentiate an x, I'd have to do something, right? Because there's a whole function packed into this x, right? So the chain rule would have to apply to that function. Right? So, for example, so if I have, let's even start with that one. I didn't start with that one, I had a different one, but let's start here. And I say find dx dt. So the steps are going to be pretty similar. I'm just going to go through, differentiate, applying all the rules I need to apply. Right? So now when I say to differentiate this, how am I going to do that? What rule am I applying? Product rule. Okay, so if I differentiate x, I get what?
1 times y.
Dx dt. Oh, right? Remember now, x is not my independent variable. He is a function on its own. You think of this as x of t. There's a whole function packed into there that I don't know, right? Times y plus, now I leave the x and I differentiate the y, that gives me dy dt, right? So both when I'm doing the x and the y, I have to attach this derivative. Because now I'm not thinking of my x as the input. It itself is the output of some other input, right? I'm thinking of both x and y as outputs of some variable t, right? Plus this one.
Both the product and the chain rule.
Okay, what would it look like?
I would.
2x
dx dt
dx dt
times y
times y
plus
plus x squared dy dt. All that equals 0. Right? Now, or you could have written x prime times y plus x times y prime plus 2x x prime times y plus x squared y prime equals 0. You could have written that and that would be fine. I'm writing here for emphasis that I'm thinking of time as the independent variable, right? So when you see x prime here, it really means the derivative with respect to what, right? That's the shortcomings of Newton's notation. That prime could mean derivative with respect to anything, and you might not know. For emphasis, you might want to write it this way to show that you have to remind yourself that time is the guy that we're looking for. So now, what was I asked for in this problem? I want to find dx dt, so now what am I going to do? Isolate the dx dt. This is how we're solved for dy dt the first time. Now we're going to solve for dx dt. There's no difference. So what would I get here? How would I do that?
Subtract x dx x dy dt on both sides.
So we're going to leave this guy alone, dx dt times y. I'm going to move the middle guy over. And what about that 2x dx dt? 2xy dx dt, I'd also leave on this side. On that side, I'm going to subtract x dy dt. And
then you also subtract on both sides x squared dy dt.
And then what?
Take it out, factor out the dx.
Factor.
Factor out the dx dt, I'm left with y plus 2xy.
And divide.
And then I divide both sides.
Or you could just factor out the y from the bottom. That doesn't matter.
Yeah, wouldn't really help.
But what exactly does this dy dt actually like?
That's the rate. That's the derivative of y with respect to t.
But like,
In other words, in this context, it means to know how fast the x is moving with respect to time, I'd have to know how fast the y is moving with respect to time.
but that dy dt literally is just one variable that you could plug in.
Yeah, it's a function. It's a derivative, which is just another function. It's the derivative that describes the slope of the function y. Right.
You don't have to factor the dy dt either, right?
No, at this point, you really only kind of want to factor a fraction if it allows you to cancel stuff and simplify. Like here, if I factor out the y and the dy dt, it can't really do anything with it, so I wouldn't really bother. And as I said, the full application of something like this, we'll see when we get to related rates. The idea is sometimes you want to keep your eyes on several things at a time. Right? So you want to know if this changes, how does it affect this thing over here? And you're trying to keep both of them in sight at the same time. And that's kind of what this is for. So let's do another example here. And we'll do more real world applications. Let's keep things kind of mathy for now. Physicsy, a particle is moving along the curve. X cubed plus y cubed equals 6xy. That's called the folium of Descartes, actually. That curve has a name. There's actually a picture.
Oh man, loop to loop.
Minus 2, minus 2. And I'm focusing on this point here, which is actually 3, comma 3. That will actually work in that graph. So that's the picture. So I have a particle that's running on this track, right? So this is a track that this particle is moving over. Okay. At 3, 3, the y coordinate is changing at a rate of -1 meters per second.
Does that mean dy dt -1?
Oh, we'll get there, we'll get there. And the question is, how fast is the x coordinate changing? At this point. Yeah. That is the problem. So now we're talking about here. We're talking about rates. Right? Here you see that the unit for how fast something is changing is with respect to time. Seconds is your independent variable here. This means x is some function of t, and y is some function of t. I can tell me at what time we are, and I can tell you what the x coordinate is doing or what the y coordinate is doing separately. Right? And so, so what information do we know so far?
Rate is -1.
We know how fast the y coordinate is changing. What they just told us was dy dt, right? Or y prime for shorthand, right? When it's understood, once you have it fixed in your head that time is your independent variable, you can write y prime without consequence. So yeah, so I know that is -1, right? They're actually telling me the rate. Right? What else do I know?
The equation.
I know that equation, yeah. Any other information?
Point.
I know the point. I know that x equals 3 when y equals 3. What do I want to find?
The rate of dx dt.
Dx dt at this point. Okay, so let's get to it. We know the relationship between x and y, so let's start there. X cubed plus y cubed equals 6xy. How do we get the rates in there?
It's
X squared
Right, start differentiating. 3x squared
dx
dx.
dt
dx dt.
plus 3y squared dy dt and 5
Okay, which gives us, do it now.
You can take the
6 derivative of x
one.
dx dt
dx dt. Leave the y plus.
dy dt.
6x.
Nope.
No, you did it.
6x dy dt.
Yeah.
Okay.
Why is
now
it 6x?
Why is it 6x?
You keep the 6, you can differentiate it with a separate.
Right, so 6 stays here because it's a constant multiplying a function. You do the product rule inside brackets. So you differentiate the x, leave the y, plus you leave the x, you differentiate the y. At the end of the day, the 6 distributes.
Well, first thing, you can actually divide both sides. You can actually divide both sides by 3.
I could.
So that means we just get. Then we need to find dx dt. So that means we subtract 2 dx dt of y on the right side.
What I would do at this point, I don't really need to find dx dt as a function, right? I need to find it at a certain point. What I would do, I'd start plug stuff in at this point. It's gonna be easier for me to just move numbers around and manipulate them conceptually than to moving all this stuff around, taking forever to write this stuff down. Alright, so I just plug in. So what do we know so far? X squared. Do I know what that is?
Yeah.
That's 3 squared. I know x is 3. dx dt. Do I know that?
Yeah. No, we're finding.
No, that's what I want to solve for. So that guy stays here. Plus y squared. Do I know that? That's actually 3 squared. dy dt. Do I know that?
-1.
That's actually minus 1 equals 2 dx dt. Don't know that. Times y,
3.
which is 3, plus 2x
3.
dy dt. Do I know that?
-1.
Right, so at this point, I know that 9 dx dt minus 9 equals 6 dx dt minus 6. Now what?
Solve for dx dt.
How?
You get it.
Okay, how?
You can add the 9.
Okay, can move a 9 to that side. 9 minus 6 will give me 3.
And then you can move the 6 dx dt.
6 to that side. What would I get?
Negative.
3 dx dt.
Yeah.
No, it's the same.
Alright, I have 9 dx dt minus 6 dx dt.
3 dx dt.
It's 3 dx dt. Yeah. 9 apples minus 6 apples. So
And then
dx
cut-
dt is what?
1.
Yeah, just divide both sides by 3 at this point. So you get dx dt is equal to 1. Which basically means on this curve, at this point, 3 comma 3, right? The y is actually moving downwards, while the x is moving that way. Can I see that? Y is decreasing. That's what a negative rate means. X is a positive 1, which means it's increasing. So you know that the particle is actually moving in that direction, right? It's traveling around the curve this way. Right? You can actually tell the direction it's moving in, which is actually another important application to physics and motion and all that stuff.
Wait,
Yes.
that makes sense considering that we were trying to find the derivative, which means literally just the slope of the tangent line at a certain point.
Mm-hmm. Yeah, but more than that, even the signs of our numbers give us interpretation, right? The sign of that means you're increasing because it's positive. The dy dt was negative, so that means decreasing. So it means in terms of even directions, you know that your y value is decreasing, it's moving down, while your x value is increasing, it's moving to the right. So yeah, that's just a small. We'll actually be doing tons more things like that in more real world context, but that's like related rates, which is I think that's still chapter 3, 3.6 maybe. But that's after the second test. Okay. Another important thing that we want to learn today, log differentiation.
Oh boy.
Logarithmic differentiation. Again, we're throwing logs into stuff. You might be wondering, what's the point? When to use. There are two scenarios where you're going to want to use log differentiation, where I'm going to describe to you right now. One is there's a variable in the power. So for example, if I ask you to differentiate something like 2 to the x, right? Or even a lot worse than that, x to the x, which was actually a bonus on the quiz.
What was the answer?
Well, we're going to do it now. There's another situation where we want to use it. The other rules are just way too annoying to use. I'll give you an example of that as well. Just to keep things consistent so I don't actually do. Like if I ask you to differentiate this. And of course something a lot messier. Don't want to scare you too much at this point. Now we do have rules that we can deal with this, but let's make this a little bit more challenging. I can throw like some e to the pi's in there or something.
No.
So the idea is we do have rules to deal with this, right? You could just do the quotient rule. But notice that while doing the quotient rule, you're going to have to do the product rule. While doing the product rule, you're going to have to do the chain rule. So you're like, holy crap, I'm going to have to do a quotient rule. Inside of that, I have to do the product rule. And inside of that, I have to do the chain rule. Doesn't sound like a lot of fun. Something like logarithmic differentiation can help you in that situation, right? So there are two main situations. If there is a variable in the power, or if something is just way too annoying to use the quotient rule and product rule and chain rule on. So here's the method. 1. Take the log of both sides. As in the natural log of both sides. 2. Differentiate both sides implicitly, which now we know what that means. 3. Solve for y prime, as usual.
What do you mean natural log?
ln.
Oh.
Remember, our logs can have different bases, right? So when we say natural log, I'm talking about log to the base e, the ln log. Use ln since we know its derivative. By the way, we proved the derivative of ln using implicit differentiation, actually. All right, so if I say y equals ln x, this would mean 1 over. Well, to solve this without, to solve for the x, what would I do? You could actually, this actually means that e to the y is equal to x, right? So at this point, I can differentiate implicitly using the rules, including the rule that was on the quiz, because I know how to differentiate exponentials at this point. This is just going to be the original function times the derivative of the power, right? That side derivative of x is just 1. Right? This is also implicit differentiation that's happening here. And so my y prime would just be 1 over e to the y. Well, what is e to the y? That's x. Right? That was why the derivative of ln was 1 over x. Right? It's actually implicit differentiation, which now that we learn, we can actually do it. Right? So I actually know how to differentiate an ln, which is good. Right? And of course, this means that the chain rule tells me how I can differentiate ln of anything. So,
Professor,
yeah.
so does it stand to reason that the derivative of ln of 2x would be 1 over 2x?
No, you'd apply the chain rule. It would be 1 over 2x times 2. right? With the chain rule, right, if you have the derivative of, if y is ln of something else, then the rule says you differentiate the outside and you multiply by derivative the inside. So if you had y equals ln of 2x, then your y prime would be, this now 2x is an inside function. So it's going to be 1 over that 2x times the derivative of 2x. So it'll actually also give you one practice. Which, by the way, that will of course always work. Right, ln of c times x, the derivative, is always just 1 over x. And you can do it by that, or you can just remember what this means. This just means ln of c plus ln of x, and that guy's a constant. He's going to go to 0 when you differentiate. Right, so there are tons of ways you can see that. Anyway, let's move on. So now let's say you're faced with this guy, y equals x to the x. Now that's going to be a problem. Why? Because we're OCD at this point and we're paying very minute detail to our rules. And I know that x to the n and x to the x are very different things. This is a constant, it's a number, this is a variable, right? I know a rule for this, I do not know a rule for that. So I'm not going to do something like bring the x down and subtract 1 from the x, because that's not what this rule says. The rule says if there's a constant, I can do that. Here we don't have a constant, right? The fact that there's a variable in the power is a problem. But hey, we know a really nifty rule about how to get rid of powers, don't we? Log, right? I know if I take the log of something to a power, what happens? I can take the power down, right? Using that fact is how we're going to differentiate this. So what we're going to do is we're going to take step 1, take the log of both sides. So I take ln of this side equals to ln of that side. Not much I can do here, but what can I do here?
Take the x down.
I can take that power down by the log rule. Now I don't have a variable in the power anymore. Now I differentiate. What's the derivative of this?
1 over y equals,
Nope.
dy dx.
dy dx multiplied by y prime. Remember, y is a function of x. So I have to apply implicit differentiation is what we're doing here. Okay, how do I differentiate this?
you would do product.
Product rule. I have one function times another function. So I'm going to differentiate this one, leave that one alone, plus
Leave the
leave
first
this
one alone.
one, differentiate that one, which I know now is 1 over x. So x cancels x. So this just gives me y prime over y is equal to ln x plus 1. And now, last step, solve for y prime.
Do you multiply both sides by y?
Just multiply both sides by y. So y prime would be y times ln x plus 1. Now y was actually this function. So therefore my y prime is x to the x times ln x plus 1. And that's the derivative of x to the x.
Wait, what was that last part?
Which part?
The last 2 steps on the second part.
Right, so here is what I have. I know I want to solve for y prime. So I multiply both sides by y. So I get this. But then my y, I actually know what that is. So I just plug this back into the y to get that. So now I have my answers in x's. By the way, any rule where you see, any rule I gave you guys where you see like a variable could be in the power, it was all derived using something like log differentiation. So if I ask you about what is the derivative of a to the x, right? What we actually did was y is equal to a to the x. I ln both sides. So now I have ln y is equal to x ln a. Differentiate this side, I get y prime over y. Differentiate this side, I just get ln a, right? Because this is a constant. Derivative of constant times x is just the constant. And this means that my y prime is y ln a. But what is the y? It was a to the x. So this means that y prime is equal to a to the x ln a, which now is where the formula came from. The derivative of a to the x is just a to the x ln a. That's where it came from. It was using log differentiation. And of course, you can replace x with u, and you can just apply the chain rule directly there, or you can even do it without it. So something more general, like this is a function, I could just apply the chain rule directly and get it. Or I could have said something like ln y equals u ln a. So this means if I take the derivative of this, I just get u prime times this. Right?
Ulna. Wow. Ulna. Like U-L-N-A.
Yeah, well now. So y prime would be y times u prime ln a. Thanks for, I've never realized that.
Ulna, yeah.
Right, and so that's where that formula came from. So now we're seeing, with implicit differentiation and log differentiation, we're seeing where all these formulas came from that I told you about a while ago.
I have a question.
Yes.
What's e to the u?
Oh, u is just a function of x.
No, e to the u?
E to the u?
Yeah.
The European Union.
That's EU. When I wrote this, I meant u is a function of x. That was what it was defined as on the paper. So if you want that, it's just going to be u prime e to the u. Right? I'd follow this rule. So it's just u prime e to the u ln e, but ln of e is just 1. So you just end up with that. So that would be the completion of that rule. There is a slightly different way to apply this. And I'll show you an example of why we might care. Is to use the fact that e to the ln of anything, right, is
That anything.
that anything, right, that thing, right? So another way we could look at something like x to the x is to actually rewrite it with an exponential in it that I know the rule for, right? So remember, we know at this point that the derivative of e to something is just u prime times e to the same thing, right? Just mentioned it here, which we proved here. So if my y is equal to x to the x, what I could have done is just say, oh, this is just e to the ln of x to the x, right? Which is, this guy, I can bring the power down, right? X ln x. And so now, I can actually do y prime, right? Now what is y prime? According to this rule, I take the derivative of the power times the original function. The derivative of the power, well, that I use the product rule for. So I differentiate x, leave this, plus, I leave x, differentiate this, so I get 1 over x, I get that plus 1, times the original. Well, what is e to this? Well, that was just the first guy. Right, e to the ln of blah is just going to end up being the first guy that you rewrote as that. So, again, you get y prime equals ln x plus 1 e x to the x. Why is that useful? For something like this, maybe. So if someone asked you to find y prime, and they told you that y is equal to x squared plus x to the x.
Oh.
Now, how would you have done that? Because sure, I'd want to be able to add two functions together. What would you do? So now you're looking at it like, that guy's no problem. That guy, but then we didn't know what the answer should be yet. How would you tackle it? What would you do?
Would you differentiate and then times the dx dy?
Okay, I'll wonder something not to do, which I've seen over and over. So students will see this, and a lot of people recognize, oh, there's a variable in the power, I should use log differentiation. And they do something like this.
Log. Oh.
And that is so wrong. Can you tell me why that's wrong?
Because that doesn't really help that doesn't help you from.
No, if that was true, that would be fantastic. Like this I can differentiate no problem, and that I can differentiate no problem.
But you can't differentiate the
I can. So this is just going to be y prime over y. What's wrong with that statement? And if this was true, the derivative of that would just be 2 over x. And if this was true, I could just bring the x down and apply the product rule. And the derivative of that would be ln x plus 1.
You can't really like.
But why is this not true? What's the problem here?
If you're assuming that ln of x squared plus ln of x to the power of x is the same thing as, I don't know, x squared plus x to the power of x.
The idea is to do log differentiation. What was the first step? We had to log both sides, right? So then I would say ln of y is equal to ln of, I have to log the entire side.
Yeah.
Now, doesn't ln distribute across a sum?
Mm-hmm.
It doesn't. Which is what, when you write this, is what you'd be thinking, right? So it's actually not true to say that this is the same as that, which is a very common mistake. So don't do that. If there's a sum of things and you don't need, like there's a sum of things, log differentiation directly will not help you. One way to tackle this is to split things up. Right? So if you're faced with y equals x squared plus x to the x, you kind of split into two things, right? Here's your f is equal to x squared. You actually know how to differentiate that. That's just 2x, no problem. And then separately do g is equal to x to the x. And then you figure out what that is. So you ln both sides. Right? You get ln of g is equal to x ln x. And then you get to the point that g prime is actually equal to ln x plus 1 times x to the x. And at that point, when you know what they're separately, you can come back here and just say that y prime is the derivative of that plus the derivative of that. Right? You'd have to actually do it separately, right? Because the ln of a sum, you can actually break that apart. So what you do is you break the functions apart and only do log differentiation on the part that you need it. Do whatever else on what you don't need it. So what something like this is useful for is it kind of saves you from the need to break something apart. So in other words, if I have y equals x squared plus x to the x, what I could have instead done is rewrite this as x squared plus e to the ln of x to the x. Just rewrite that guy.
And then bring the x down in front of the x.
Right.
Yeah.
And now I can just apply rules that I know. I don't have to split things into two or anything. This is power rule. This guy is the derivative of the power times the original function. So derivative of the power is product rule. So you get ln x plus 1. And so now I have 2x plus ln x plus 1 And this guy is just a rewrite of that guy. So I can put it there.
Why can't you just cancel the E and the L in the beginning?
Where?
The second part.
Here?
Yeah.
Well, if I cancel again ln, what does that do for me? It brings me back here, which I couldn't deal with. Right? The point of doing this is to get it into a nice form because I know how to differentiate e to something. Right? I have a rule for that. I just differentiate the power multiplied by the original function. So either way is fine. Just pick whichever way you like. This is another way. Pick whichever way you like and always do that way. Right? So if you like writing e to the ln of something and just applying the rule that you already know for e, that's fine. But there are other times in sums you just break it into pieces and do log differentiation on one part. Let's do the last example. Let's do that painful quotient rule, product rule mess. So if I have y equals, I think it was radical x times x cubed plus 1 to the, what was it, 2/3?
Something like
It was messy. 3 halves. Over, I think it was 2x. 7. 2x squared plus 1/3. Okay. So yeah, technically I could do quotient rule with the product rule and the chain rule. Doesn't sound like a good time. What instead I could do is I could just ln both sides. And what would be the point of that? Because I felt like. How does that help things?
Bring the power down.
Bring what power down? I can't get to that. I could only bring a power down if I'm right beside the thing that has the power, right? Then I can bring that down. If there's something in front of it, I can't. That rule doesn't apply. Pay attention.
Well, you could change the x to a 1/2, the radical x.
I could have done that, sure. Now what?
You can split them into
How?
different portions,
Oh.
like pluses and
Right.
minuses.
We have those rules for ln of divisions and ln of multiplications and all that, right?
Oh, yeah.
So the division, this is just ln of x to the half, x cubed plus 1 to the 3 halves, minus ln of 2x squared plus 1 to the 7. This I can split further. This is just ln of x to the half, right? In fact, I can bring that half down in front.
Okay, so this.
Plus, this part I can bring down in front. ln of x cubed plus 1. Minus, this 7 I can bring down in front. ln of 2x squared plus 1. Now, together, this would have been incredibly annoying to differentiate, right? However, now when these are break into pieces, these are pretty easy. What's the derivative of this one? Derivative of ln x is what?
1/2.
Remember, you have an ln y here, first of all, so that's just going to be y prime over y. Now you focus on this side. Derivative of ln x is just 1 over x, so you just have a half times 1 over x. Move on to the next one. You have 3 over 2 times. What's the derivative of ln of x cubed plus 1? You put the thing on the bottom, and you put its derivative on top. That's the derivative of ln, right? It's 1 over the thing times the derivative of the thing. By the chain rule. What about the derivative of this one? So then it's minus 7 times derivative of this. Just put the thing on the bottom, and then you put the derivative on the top. And so now your y prime is just y times all of that, which means your y prime is equal to, the y was this whole thing, times 1 over 2x plus 9x squared over 2 times x cubed plus 1 minus 20x over 2x squared plus 1.
Professor.
So a lot of it, this part here was just algebra. In theory, it should be easy for you at this point. And the derivative of each of these individually is no big deal. Try doing this by the quotient rule, and you will start to appreciate this.
Can't you just do that? Can't you just do the product rule by just having radical x, x cubed plus 1 to the power of 3 halves plus 2x squared plus 1 to the
Yeah,
power
you're
of
gonna get
7?
You're going to get 1/2 x to the minus a half times this, plus 3 over 2 times this to the half times 3x squared times this minus this times the derivative of this by the chain rule, which is 7 times 2x squared plus 1 to the 6 times 4x all over this guy to the 14th power. And then you're going to have to simplify that. And it'll be really easy for me to make this a lot uglier. This is just the first example.
And how is that not ugly?
Because this is the answer. Like, you wouldn't need to do anything.
But like, let's just say like the derivative is actually like the slope of a tangent line. So now let's say you told me find the slope of whatever of that function.
Yeah, just plug in a number here. They all become numbers. They all become numbers. And of course, in theory, it'll be an easy number. Like, I could say, find out when x is 0. Then this is just 0. We're cool. Or find when x is 1. It's not going to be a big deal.
Or maybe on the final I'll ask you find the slope when x is like 3.5.
Anyway, that does it for this section. So tomorrow we'll look at all the homeworks up to 3.5, and we'll also do 3.2. Yeah, that's it. I gave you guys your tests back in your homework, so look over them. If there are any problems with them, let me see them tomorrow.
Can you tell us what's going to be on the next